Hi, welcome back. This is going to be a lecture on stereolithography. So this will finish up our series on stereolithography and liquid-based processes today. So I'm going to switch to share my screen. And from there, we will do some note-taking and switch back and forth between different venues. All right. So as we look at stereolithography, all right, there are three broad categories of error. In stereolithography. And some of those are also in additive manufacturing in general. All right, so one is representational error. And this is just caused by representing a surface with an STL file. Okay, and so that is simply just a CAD to STL conversion error. We'll talk a little bit more about that when we're in the design for additive area, and it can generally be reduced by specifying tight tolerances on your STL file. Okay. And so this is really common to all additive processes. Okay. The second is process planning error. Okay. And so those are caused by the way you planned or prepared the build. Some of them are actually unavoidable. Okay, so an example could be stair stepping. Okay, and this is a prominent error in additive manufacturing. So if you wanted to build, something that was, say, shaped like a pyramid, right? You have no choice but to stair step that design, right, as you're building it up. Okay. And so this is a problem in stereolithography, just like it is in other processes. All right, and so both of these are kind of common to most AM processes. Okay. Now let's look for number 3. Let's look at process errors. And so every process also has its own errors that are inherent to it. All right, but we're going to look specifically at stereolithography. And so these are caused by the physics or chemistry that's inherent to the process. Okay. Physics, the chemistry, the machine, the materials that are inherent to the process. Okay, and so there are several examples here for SLA, for stereolithography, right? And we'll look at a few of those, right? So some of the ones that I want to look at, the first one is we're going to call overcure. Okay. And we can also look at the same time, print, what's called print through. All right. So let's look at those a little bit. All right. And so one of the things that happens in stereolithography is, let's say we wanted to build this part, right? Okay. let's say we want to build this part for some reason. The build platform is down here. So this is our platform that we're building on. Okay. And remember, in stereolithography, you typically have support structures that so attach the part to the supports to the build platform. You'll also have some support structures in here, right, that attach the part down to the build platform. All right, but what will happen here is as you build up this part layer by layer by layer, right? As you build up this part layer by layer by layer, what you're going to get, let me just erase these support structures for a second so it's a little bit clearer to see, is you're going to get a little bit of what's called overcure or print through. Okay? So this is what's called overcure or print through. Okay? And what that means is just that you've got additional exposure that a laser cures beyond or past the layer thickness that it's trying to cure. All right. So this is just okay. So that's the depth of the laser. So that's overcure, right? And print through is just additional exposure. Okay, from layers above that feature. Okay, so you get a little bit of penetration of that laser underneath the layer that you're trying to print. All right, so that can cause a little bit of dimensional inaccuracy, especially on downward facing features. So typically the cure here for, cure through, right, is the newest SLA build styles. Typically shift layers up to compensate for overcure and print. All right, so the next one that we want to investigate is another error. Another example here of a process error in SLA is shrinkage and accompanying warping and curling. Okay. So what typically happens here is, so one of the ways that, let's take a look at one of the original SLA scan patterns, and that will help you understand a little bit about warping and curling and how that comes from shrinkage in a stereolithography pattern. So one of the original earliest scan patterns in SLA was something called the weave. Okay, and you'll see why they call that the weave in a second. So basically it consisted of a couple of parallel scans. So let me try to draw this out for you so you can see it here. Okay. So here, kind of what you can see is that it's got two sets of laser scans. Okay. So the first set here, we've got a couple of axes on here. Let's call this X and let's call this Y. So the first set is parallel to the X-axis. Okay. And that would have a cure depth, so CD, equal to the layer thickness minus, say, 1 mil. Okay. And so this is cure depth that you want to go. And this is layer thickness. So it's almost as thick as the layer that you want, but not quite. Okay. And then the second one is parallel to the y-axis. Okay. And it's also with a cure depth equal to the layer thickness minus about 1 mil. And so then together, they will actually cause the layer to adhere to the layer below. So it's two sets of laser scans per layer. Okay. So the first question you might ask is, why do we have this spacing in the XY plane, right? So the reason they're spaced a little ways apart here is basically to prevent the laser lines from interfering with one another while they cure and shrink. So as they start to cure, then they start to shrink because the polymerization causes the resin to shrink, and the shrinkage can be substantial, several percentage. And then the next question you might ask is, why is the cure depth less than the layer thickness? All right. And the reason is that that's true. So let's write that down. Why is the cure depth less than the layer thickness? Right. And it's basically, the reason is to separate, okay, the majority of curing and shrinkage of a layer from adhesion to the previous layer. Okay, so what will happen is, as you scan, right, if I draw out this scanned region from above, right, what's going to happen is it's going to scan these things first, right, and then it's going to come, so these are scanned first, these X, and then they start to shrink, right, and they'll start to shrink primarily in the X direction, all right, and then you'll come back and then you'll scan these second, right, right, and then you'll get a lot of shrinkage in the Y direction as well, okay. But the good news is that a lot of that X direction shrinkage from left to right will already have taken place before you go back and scan in the Y direction. And so you basically get a wave of shrinkage sort of from left to right, and then you get a wave of shrinkage from top to bottom in the Y direction, all right? And so the idea was that, you know, this X direction shrinkage could take place while it's curing before the Y direction scans came along. And so that shrinkage in the X direction could take place without any adhesion to the layer below, because the cure depth is not deep enough, right, to adhere to the previous layer. The cure depth is less than the layer thickness. The only time the cure depth is deep enough to actually adhere to the next layer is when you then come along with these Y direction scans. So the idea was then that you could allow some of that X direction shrinkage to take place before you come along with that Y direction scan and adhere to the layer below. So it basically just eliminates a little bit of the residual stress that is placed on the layer below and minimizes the warping and curling just a little bit. The problem is you still get quite a bit of shrinkage. You still have half your shrinkage taking place when those Y direction scans come along. And so you still get curl and you still get, some warpage of your part. And that's not a good thing. All right. So one of the things I want you to remember here is, if you remember from before spring break, the cure depth, right, is equal to something called the depth of penetration times the natural log of N E max over EC, right? And this DP, this depth of penetration, and this EC, right, this critical energy, both are properties of the material. Okay? But E max in this case is a property of the laser in the scan. Okay? Where this PL is laser powered, W naught is spot size, and VS is scan velocity. All right. So as we speed up the scan velocity, right, E max goes down. When E max goes down, the cure depth goes down. Right. And so one of the things that we can do is, if we have multiple scans, right, then N here in this case is the number of scans that we have. The N in this equation is the number of scans that we have. So one of the things we can do is take advantage of that relationship to help scan a stereolithography part, a layer, and maximize the amount of shrinkage that can take place before it adheres to the layer below. All right, so if we look at the current scan pattern, so the cure for this problem, cure for shrinkage-induced warping, is a newer scan pattern called ACES. Okay? And so if we look at, if you want a closer look at ACES, look at figure 413 in the Gibson book, first edition. Okay. And so what happens here is that we get a number of scans across the build envelope. Okay, so if this is, so we scan, so this is a measure of energy induced, right? This is E total, right? And so what we do is we get a number of scans, right? We'll start to scan, and then we'll come back and we'll scan some more, right? And we'll scan some more. And this whole entire thing, if we add it up, right, we'll get a very large amount of energy that gets placed into the resin, right? And if we look at, if in this direction we look at cure depth, right? Then for each of these scans, we get, a small cure depth, right? We can do that over and over again. For each of these individual scans, we get a small cure depth, but then we add them all up, we get the full cure depth, right? So this is the CD total, which equals the layer thickness, okay? But this is the amount of cure depth that we get, we'll call that CD naught maybe, from each individual scan. So what we'll do is we'll take each of these individual scans, and each one starts to cure the material. The material shrinks, and most of that shrinkage can occur before you come back and add that final pass that finally gets the cure depth deep enough so that it adheres to the previous layer, right? And so that's one of the ways that they can avoid too much shrinkage-induced warping, because most of the curing takes place before that final set of scans, which makes the cure depth finally deep enough to actually penetrate into the previous layer. So most of the shrinkage has occurred, most of the curing and shrinkage has occurred before you do that. Okay. All right. Okay. So one of the other That also helps another one of the example errors that we get in SLA, which is incomplete polymerization. Another example error in SLA is incomplete polymerization. Okay, and so these new scan patterns help. You're distributing, because in this scan pattern, you're distributing the scans all across the surface of the part, getting really, really good curing, nice uniform energy delivery all across the surface. Whereas in some of the older scans, you can see it's more of a checkerboard pattern, and you're not getting energy delivered to completely cover the space. And part of that is because you wanted to allow some space for shrinkage, but it also means there's a lot of incompletely polymerized resin in there. And let's talk a little bit about what that incompletely polymerized resin, what's the deal with that? Why is that important? Why does it matter? All right, so we need to know a little bit about photopolymerization. And this is really important because it's one of the weaknesses, I would say, of stereolithography parts. They often don't age well. All right, so photopolymerization, let's just talk about that for a second. Right, that's the process by which photopolymers are cured. Okay, and it's basically a process of linking lots of small molecules, which are called monomers, into chain-like large molecules or polymers. Okay, and it's initiated by a photochemical process. Okay, and that photochemical process causes something that we call cross-linking. Okay, all right, so typically what you have is you have a laser. So this is your environment. This is the resin. Okay, we have a laser that's impinging upon that surface and providing the ultraviolet light that's needed for this cross-linking process to happen. And inside the resin, you have a combination of what are called photoinitiators. You have a bunch of what are called monomers. Okay, and so one of the points of the ultraviolet light from the laser is to take these photoinitiators, to turn them into free radicals, which then bond with the monomers and start a propagation of a cross-linking reaction. So a PI here is a photo initiator. Okay. An I is something we're going to call a free radical. And M is a monomer. Okay. So a photoinitiator converts light into chemical energy, right? Okay, converts light into chemical energy in the form of free radicals, okay? In the form of free radicals. Those free radicals are basically molecules with unpaired electrons. Okay, so for example, hydrogen, right, could go to 2H plus, right? And an M is a monomer, right? So these are the basic building blocks of our polymer chains, all right? So what happens is then that photo initiator, once it gets light of the right wavelength, then becomes what's called a free radical. Okay, and that's a free radical. Okay, that free radical, all right, then starts to bond with monomers, right? And so that's the free radical bonding with monomers, all right? And then that chain starts to propagate. So we start to propagate that. And then eventually what you'd like to see is that it terminates, all right? And so then you get an I, M, 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 I, right? And that's a terminate. Right? It eventually forms a very, very long chain. It cross-links, and then it terminates by combining with another free radical chain, right? And so there are several different reasons why it might terminate, okay? So one reason is what we call recombination, okay? And that's when two polymer chains merge by joining two radicals, okay? And that's really what we've illustrated just up above. That's what we'd like to see, especially after these chains become quite long. The second one is disproportionation. And that happens when you cancel one radical with another without joining the monomers together. Okay, and so that's not something that you want, because then that means that you've basically just used your laser light to form these free radicals, and the free radicals just combine together without forming a polymer chain first. And that's not good. The other thing that can happen is something called occlusion, where the free radicals become trapped within a solidified polymer. Okay. So you still have free radicals, but they don't have enough mobility to react. Okay? So sometimes those free radicals have already started to form one of these polymer-rich chains by combining with some monomers, but they never actually find another free radical to combine together. And so one of the things that scientists think is that you have these free radicals that are trapped inside the material, an eventual reaction with oxygen over time could be one of the causes of aging. So a lot of times these stereolithography parts, the materials do not age well. So they yellow with time, they become more brittle with time. And so some people, for example, have talked about placing stereolithography parts in a window where sunlight comes in. And over time, they become so brittle that you just pick them up and they almost disintegrate in your hand. And so that's one of the real downsides of stereolithography, these photosensitive resins, is the fact that they sometimes don't age well, right? And so that's a downside. The positive side, though, is that often these stereolithography parts, because of all the control that we have over the process, and let's go scroll back up and remember how much control we have to be able to solidify, for example. We can get really good surface finishes. We can get reasonably good accuracy as well. And so those are a couple of the things that stereolithography in particular is known for, okay? So this idea of photopolymerization, of using light of a particular wavelength, in the case of stereolithography, it's ultraviolet light, to cure resins, to cross-link resins and solidify them, is not unique to stereolithography. So let's just take a quick look here at a couple of other processes that are important to talk about. All right. So one of the other processes I wanted to give you some exposure to is a process called Objet. Okay. Objet is really the trade name. There's Objet Connex is another name for it. Objet was an Israeli company that basically founded this particular process and then became acquired by Stratasys a little bit later. And so now Objet and Stratasys are under the same parent company. The way it works is, if you look at this slide, you can kind of see we've got yellow and white materials here. The white material in this case is a support material. The yellow material is the build material. And so what's happening in this blue carriage that moves back and forth, in this case along the x-axis, right, is that it jets down material. This is photosensitive resin. At the same time, it immediately follows with an ultraviolet light source. You can kind of see it in purple in this particular diagram. And that ultraviolet light source then cures the material very quickly. Typically, the support material is water soluble, so you'll often put it in some sort of water jet or water bath to dissolve away that material. The other thing they do here is, because you're jetting down the materials, there's no reason why you can't jet down more than one material. And so the Objet process takes advantage of that, and they often have a couple of different materials. There's like a Tango black and a Vero white, one of which is really flexible and the other of which is very rigid. And you can lay down either material. You can also start to blend the materials. So you can have materials that are really flexible, really rigid, and then almost anything in between. And so that gives you this ability to actually do multiple materials in a single build. You've also got really accurate features, very good resolution as well. So you can get 600 micron features, even less than that. The layers are very, very thin, 100 microns, even less than that sometimes. And so that can give you some really interesting parts. Let's see if we can get the video to play here so we can take a quick look at what one of these processes looks like. Okay. All right, so let's skip the ads, get to the part, and I'll kind of narrate as we go along. Otherwise, we've just got music in the background that's not particularly interesting. So Objet, this is a Connex 500, which is pretty similar to a machine that's still being sold. Again, the advantage here is this is one of the first processes we've looked at where we can get different materials with different mechanical properties printed in the same part. It's a fairly office-friendly process for the most part. You bring in STL files, but then you can assign different materials to different parts of the STL file. You can also, you'll see that they've added a black material here in some areas. The rest is going to be a white material. The black material here is much more flexible. You can also grade the material from place to place. So it's not a binary, one material, two material. It can be graded as you go along. You see the material is a liquid resin and it's jetted. So there's no powder to deal with in this particular process. In this case, what they're doing, you can see the glowing light, and the glowing light in this case is the ultraviolet light that's curing the material as it's being deposited. So this is a print head with inkjet style print heads that's laying down the material. And then immediately following with this UV light cure, right? It's all embedded in the same head as it moves across. So here you can see it start building up these parts. In this case, they looks like they haven't made full advantage of the process. They're doing two different materials in a sort of a binary combination. And you'll see towards the end that the black material in this case, I believe, is much more flexible than the white material. It's a reasonably office-friendly process once those parts are built. Then the next stage is to remove the parts from the build platform. And so typically they'll have a thin layer of support material in between the part and the platform so that they're reasonably easy to remove. And you can see that here. You can almost see that little sign of the support structure underneath the part as you're removing it, in this case with a spatula. And then they'll scrape the rest of the material off of the build platform. They'll clean it with a cleaning solution to make sure there's no residual material left on the build platform. And so you get good adhesion from the next build, right? So that process of building is really reasonably office friendly. Then you have to have some water jets in an adjacent tank. And what these water jets are doing are dissolving support material. There can be some difficulties here with really small features, although they say, you can get, features that are, a few much smaller than those that you can get in SLS or SLA. You can damage those when you start to remove the support structures. Right? You can see the really good surface finish and the good resolution that you get from this particular process. Okay. All right. So so the next thing that I want to talk a little bit about is here. Well, here you can see a couple of examples of some object parts. So in this case, you can see this is just an example that I thought might be a good one to show you, because you can see the hard plastic toothbrush and the soft bristles. So it really kind of shows off what the object's capable of doing. You can also see on the right are some images from a paper where they've optimized a part, a flexible structure. I'll make sure this paper gets uploaded to Canvas for you guys to take a look at. But you've got black material where you want it to be really flexible and white material where you want it to be very rigid. And so you can actually get some compliant mechanisms, things that have a lot of motion associated with them, using this process. Here's another process that you may have heard of that is very much a photopolymerization process. It's one of the processes that it's gotten more venture funding than almost anything I can think of in recent years, and it's a process called CLIP from Carbon3D. So you may have, if you've been paying attention, there's been a lot of news releases and other things like that that show the CLIP process in action. So I encourage you to take a look. There's about a 25-minute video at this particular address here. You can see up here in the upper right of this slide, and you can take a closer look at the CLIP process in particular. Let's see if we can get a video going of the CLIP process real quick, just so you can see what it looks like. Okay, so this is as you can see in the bottom left, a 7x speed video from Carbon3D. These parts build in a vat of resin. So this red area here is that vat of resin. It's being illuminated from below, in this case using a continuous image, more like a video than a scan or a 2D image. So it's a continuously variable image that's being projected from below. Oftentimes when you pull parts up from below, one of the difficulties you have is they tend to stick from whatever surface is down there that's the bottom surface of the vat. In this case, they've got some oxygen permeable membranes at the bottom that serves as the base of the vat. And what that does in this case is those oxygen permeable membranes allow just a little bit of oxygen in just at the bottom of the vat where the light's coming in from below. and that oxygen prohibits the photopolymerization process from taking place. And what that does then is when it prohibits that photopolymerization from taking place, it keeps the part from sticking to the bottom of the vat of resin. So here you can see in this image, the orange here is the oxygen permeable window. And so there's a really thin layer of oxygen in this resin next to the window that prevents it from solidifying and curing in that particular region. But once you move away from the window, there's not enough oxygen to prohibit the curing and the cross-linking. And so then you get the parts to form really well. You have an imaging unit, of course, that brings that light up from below. And so on the right here, you can see this is one of the original articles in the journal Science that introduced the process. You can see that typically you have a stair-stepping effect from curing layer by layer by layer. In the clips process, what happens is that you're continuously adjusting the image as the part emerges vertically out of the vat, so you don't get the same stair-stepping process that you might otherwise get. Okay. So another process that you might be interested in is microstereolithography. And so over the last 10 years or so, several researchers have been very successful at building really small-scale stereolithography processes. And this is an example of one from the University of Texas at El Paso, one of the earlier systems. And up here in the upper right, you can see a little bit about how it works. You've got an optical fiber that's coming in, and that red trace in the image is the laser light. It's hitting off of a DMD board, and that's a digital micromirror device. And you can think of it as a sort of a pixelated surface. And those pixels are very, very, very small, and you can turn each one on and off, which allows you to control the light that gets reflected down onto the build, into the build envelope very, very precisely. And so then here you can follow that trail of light through some optics and mirrors and down into a tiny resin vat. And here you can see down here on the bottom a couple of the images of some of the things they've been able to build using this process. And this is just for illustration. You can see this is a tiny chess set next to a dime, which I find to be very remarkable. So with this process, you know, chess sets are great for illustrating, but not necessarily the most functional thing. They've done things like, for example, they can do specialized needles that you might use, for example, to insert something into an eye. Those needles can have corkscrew patterns in them to maybe combine different medicines together as they're being inserted into the eye. So there's a lot of really cool stuff that you can do with this process. Okay. And here, if I can get it to come up, here we go, are just a couple of really cool, you've seen some of the snap-through structures that I've shown you from the research in our lab. Here's a couple of really cool images of some snap-through structures that were made using microstereolithography. So these are only 2 millimeters across, so each one is about the size of a grain of rice. And these curved beams actually snap through. It's pretty remarkable that you're able to do this. And this came from a microstereolithography process at Lawrence Livermore National Labs. All right, so I'll upload a few papers there to accompany some of those extra processes like clips and objects, so you can take a look at some of those in a little bit more detail. Now let's do our process comparison, morph matrix, and machine comparison for these processes. All right, so let's see. We've got page 1, page 2. So let's see, rotate it. There we go. All right, so this is where we were in terms of our process comparisons, and now what we need to do is add stereolithography to this process at a minimum. So let's start to form. Let's add stereolithography. Let's add SLA here. Let's see if I can mark. All right. So let's add stereolithography. SLA is our next process. Right, typical process variables there could include layer thickness, scan speed, right, material, of course. I guess that kind of goes without saying. A lot of these processes have material. Some of the advantages, if I could pass around parts so you could see them, you would see that the surface finish can be outstanding in stereolithography, partially because of this ability to really vary the scan speed and change the cure depth. You can almost eliminate stair stepping as well. You can have transparent parts, which can be very, very useful for example, surgery planning. So you could, for example, plan a surgery where you can see a tumor inside of a body part, and you can plan your process of repairing it. Accuracy is generally quite good on stereolithography as well. The disadvantages, based on our discussion so far, right, we've got problems with aging, right? We've also got support structures that we have to remove. Sometimes in things like object, they can be water soluble, but they still have to be removed, and they're needed. And why are they needed? Right? They're needed because you have to be able to anchor the parts down to the build platform, right? Otherwise they'll float away in the resin. So it's not like an SLS process where the powder supports everything. So that means that you also have to have some post-processing, right, to remove the support structures. It's not office friendly, so it's office unfriendly. The resins have to be handled with care. They typically aren't supposed to touch your skin. You typically have another UV curing oven for post-processing to help make sure that all of the curing that you can manage has taken place. So that's important as well. You also can't do hollow parts. In some cases, you can do that with FDM. So it's not isolated to SLA. That's also true of SLS, right? And 3D printing, those powder-based processes, they can't do completely hollow parts either, because the resin in the case of SLA or the powder in the case of SLS would be trapped inside, right? I think it's also useful to at least put object down here as well. And we didn't talk a lot about the process, but one of the cool advantages here is multiple materials, right? And graded materials, so you can grade from one material to another with different mechanical properties. You get really good surface finish and very good accuracy. You inherit some of these other problems though, right? With respect to aging and support structures and post-processing, so on. Okay, so those things get inherited. All right. Okay, let's look and also take a look at our machine comparison. So we want to make sure we finish that up and add all of the parts that we want, all the machines we want to look at, right? So far, we had gotten all the way down to lens, right? But we also, I want to add a couple of stereolithography machines. And I also want to add an object in there. So you'll have that as well, okay? So let's do what used to be called the SLA 250. Expand this just a little bit so you can see it just a little bit better. Okay. But now is what's called a Pro Jet 6000, or at least recently it was called that. They keep changing these on us. In terms of the vat size, this is a small one. So I'm going to give you kind of a small entry-level machine. In terms of the accuracy, we've got plus or minus 0.15 millimeters. So that's competitive with all the other processes that we have. And in terms of feature size, about 0.5 millimeter. And this machine is going to run you somewhere around 200K, although you can get a used one for less than that. And then there are large SLA machines. So let's do an iPro 9000 XL. Okay. And now it's called, I believe, a Pro X 950 is another name it's known by. And it's a very large machine. All right. Accuracy is a little bit better, plus or minus about somewhere between 0.025 and 0.05 millimeters per inch of height. Okay. The minimum feature size, pretty small. So you've got better feature size, better resolution, better accuracy. And last time I checked, this one was getting close to $1 million though. Okay. All right, let's put an object machine on here as well. Okay. And this will be a Connex. And it's enough to do multiple materials. So that's why I wanted to highlight this particular machine. All right, so its build envelope is 0.5 by 0.4, about 1.5 by 1.5 and then just about 20 centimeters, a few inches tall. In terms of the accuracy, it's plus or minus 0.04 millimeters. It's really quite good. And the minimum features, it says about 0.6 millimeters, but practically speaking, it's probably closer to a millimeter or so. And the reason is because when you get really small features, it's very difficult to remove support structures around them. They become very delicate. And you saw that process where they were using sort of high pressure jets to remove the support structures. All right, and so we're talking about somewhere around 250K new, maybe a little less now for one of these machines. Okay. All right, and then the last thing we want to do is our morph matrix. All right. All right, so let's finish up our morph matrix and let's add stereolithography to that mix. All right. Okay. So here's our morph matrix to date, and what we want to do is add stereolithography to it. So what we have here is a liquid material. And so that's, we're going to call this SLA. It's not really molten, it's a liquid, right? I guess you could kind of call it molten, but so stereolithography would be there. In terms of patterning the material, we don't really do that. We just have a big vat of resin that we use, but we do pattern the energy, and in that case, it's a point source, right? It's a 1D light source for stereolithography. We photopolymerize. We recoat by dipping, usually. We also do sometimes a little bit of spreading. So often they'll dip the part underneath the surface of the vat, and then they'll have a recoater blade that comes and pumps more resin across. And then finally, to support previously built material, we typically have thin trusses of build material. If we want to look at object's very much the same. It has liquid material here that it deposits down. It patterns the material here in a 2D ejection, so it's a little bit different here. It has those, instead of a point source, it has point nozzle, it has a line of jets that move across, so that's why it's a 2D ejection system. And then there's no energy patterning, it just comes, it patterns the material, not the energy. It just brings just a blanket UV light source across. It photopolymerizes, so it's the same as SLA there. It recoats typically, by spraying, okay? That's that spraying and ejection method. And then it'll use dissolvable support structures to support, the previous layer. All right. Okay. So that completes our process comparison, our machine comparison, and our morph matrix. All right. So that wraps up stereolithography. So those were our liquid-based processes, right? So if we go back to our ASTM standards, stereolithography would be that photopolymerization. Under that category, an object would be material jetting. So that was the first and only instance of material jetting where we're actually jetting materials down and curing them. And that would be an example of that ASTM process, that ASTM category of processes. All right. So that kind of closes up our entire unit of looking at solid-based, liquid-based, and powder-based processes. We've shown examples of all of the ASTM standard processes. And so next what we're going to do is we're going to transition a little bit more into design for additive manufacturing and look at some of the opportunities that it opens up, as well as some of the restrictions that it places on the process that can be captured by design guidelines. All right.